Hey, see some familiar faces. Hi. So this is Rob 101, Computational Linear Algebra. It's essentially a new course. We piloted it last fall. The team is up here with a great bit of thanks to Professor Dwayne Joseph at Morehouse, who helped us in the piloting of the course. This semester, most of your lectures will be given by Mani Ghaffari. So Mani's an assistant professor in robotics and naval architecture and marine engineering. He knows about a lot of things, but I think he knows nothing about cavitation, right? And
I don't know anything
ship
about
hull design.
Sounds like they gave me the job.
I'm in electrical and computer engineering, and I hate circuit analysis, okay? So we make a really great team here. Currently, I'm the director of the Robotics Institute. So, really happy to have you. Whoa. Was that me?
That's me. Sorry.
That was you? Oh, okay. Wow. So the course is worth 4 credits. There's 3 credits for the lectures, which are Monday and Wednesday, and then Tuesday there's the lab. We will start the lab to get you going on the Julia programming language. It's a really great part of the course. The students last year did not have formal lectures in programming. They had to absorb all of it through a sort of tutorial pre-examples before doing the actual programming assignments. We're hoping it works a lot better this year. So I want to really thank Professor Todd Shern at Howard University. So he's going to be teaching about 1 month of this material at Howard this semester. And so Todd, when your students are watching these videos, I hope they have a good time and they'll give us feedback. And then once again, saying many, many thanks to my colleague Dwayne Joseph. And then also, there's a version of this course being taught at the school at Marygrove, which is kind of a magnet school in Detroit, and it's being taught at the 11th grade. Obviously, it's a toned-down version, but our thoughts is, you know, all of this emphasis on calculus is wonderful, but it's a little bit misplaced today. Calculus was a great response after Sputnik went up, and we were worried about the Russians and satellites and rockets and missiles. But in the day and age of artificial intelligence and robotics, linear algebra is the fundamental language that you need to speak. And getting going on that will make the calculus that you learn make sense. Let's see, I think Caitlin is here. Anybody else from the team? Tribby, you're in the back. So Tribby is a graduate student. She's passed her PhD qualifying exams in robotics, so she's a candidate officially. So she's got 2 or 3 more years pounding through. She has to walk through the black pit of the unknown because research is all about solving problems where the answers are not even known to exist, much less you don't know that they're in chapter 4, okay? Because there is no chapter written on that until she actually writes her dissertation. The IA, so that's Michigan speak for instructional assistant. You might think of them as teaching assistants, but Michigan doesn't use that terminology. GSI is graduate student instructor to indicate them. So the IAs are all undergrads. They're 1 year ahead of you. So they took the course last semester. There's others on here who have not sent us their photos, but of course we know them. We get them up on the website. So they went through the course last year, and they're here to help you in acquiring the information and having a good time with the material. So Rob 101, the big thing is it combines linear algebra and and it gets you up to speed in doing, gets you up to speed into thinking like an engineer. So most of the courses that you've taken are sort of like, they're very similar to the courses you would have taken in high school, where you've got a set of homework problems that have, 2 variables, 2 unknowns, a couple of equations, etc. We're going to get you solving problems with 50 variables by week 3 in the course. So that's the big thing. That's the big difference. And that's why the Computer Science Department is accepting Rob 101 as an equivalent to Math 214. There'll be a little bit on the theoretical side, maybe that's taught more in 214, but you'll know much more about how to use linear algebra through what you learn in Rob 101. And then, if you were looking for a replacement, because maybe you're in Engine 101 learning C++ and MATLAB, you could be taking Rob 102 AI and programming, and I'm told is going to count in place of Engineering 101. So that's being taught 10:30 to 12 on Mondays and Wednesdays. And then, unfortunately, Rob 103 is already full. It's our robotics mechanisms course. So these are courses the Robotics Institute is developing to get you into robotics at an early age. Many who came before you, yes, they wanted to do robotics, but they couldn't do anything in robotics until they got to the 300 and 400 level courses. It was kind of disappointing. So we're hoping this will help get you going, and then we're going to introduce another sophomore level course next winter. Then there'll be a whole set of 300 and 400 level courses coming after that. There should be a robotics department launched in July of 2022. That's like tomorrow, okay? And for us who are doing all the creation of the department, where Monty can then have his tenure and actually be in a department where he knows a lot, okay? Instead of worrying about cavitation and hull design for ships. So yeah, so we really focus on large-scale problems. The lectures, yes, we've got to work out the problems by hand and do simple versions. So in the lectures, we'll do really easy versions. In the homework, you'll have 2 types of homework sets that go together. The first part are drill problems, which are just like the problems you had in high school with 2 variables and 2 unknowns or 3, or plot this thing, etc. But then there's a Julia programming assignment that goes with it that then takes it to scale. And once again, what I mean by scale is we're shooting towards hundreds of variables and being able to do realistic problems. Okay, so you first, oh yeah, now I know how to do all the calculations by hand. And I didn't want to do 7 variables by hand because I couldn't get the minus signs right, much less to divide by 4s, okay? But once I understand the problem, I can program it, and then once my code is checked out on the easy problem, it's probably going to work on the hard ones. So that's what we do. As my colleague Chad Jenkins says, programming equals believing, okay? When you get it working in there, it's very satisfying. As I've mentioned, we're trying to really shorten the path instead of making you be juniors and seniors to learn things like computer vision and machine learning. You're going to be able to jump in those courses much earlier. You can take them probably the 2nd semester of your sophomore year. So year 2, 2nd semester, you could be getting into computer vision and machine learning. And then it's also kind of important to us from an opportunity point of view. Many of you went to high school where you have AP credits available, but I don't know if you know this, but high school funding in Michigan, a lot of it is dependent upon where you live. It depends upon the property taxes that are paid on your homes. And so if you're in a neighborhood which is not super advanced, you may have no AP courses. And then there's lots of people who are still not encouraged to get into STEM because they're not white males like me, okay? So this course is going back and looking at what do you really need to be successful in college. And what we're saying is that even if you didn't get on the calculus bandwagon in your junior year in high school or something, it doesn't really matter. We can take you, if you know algebra, and you're smart and motivated. If you're smart and motivated, you wouldn't be at the University of Michigan. So you're at the University of Michigan, you have algebra. We can take you to a point where you guys are going to be understanding things that many of our graduate students are just learning this year. Okay, so a lot of our master students are in another course called Robotics 501, Mathematics for Robotics. And they're going to learn some of the same material that we're going to teach you. And they're mad about it, okay? They feel it's not fair for us to be giving this knowledge to students at this beginning of the stage. I know, you don't really believe it. The projects are awesome. The first project, we give you 90 megabytes of LiDAR data collected on the Cassie bipedal robot. You can see how the robots, this is the camera image moving back and forth. So imagine if you just took what the robot is seeing and you didn't correct for the motion of the robot, then you just get a big blurry image. It's like you trying to take the camera when you're shaking, okay? So we will show you how to do the motion compensation and you will build a map. That's project number 1. Project number 2, we're going to use a technique in linear algebra called regression, but we're going to use functions that are common in machine learning, and we're going to have you build a surface map of precipitation from the state of Alaska. Why state of Alaska? It happens to be open source, okay? Get all the data, that's all. That's not because we would have loved to do it for Michigan, the Upper Peninsula, but we can't. And then the last project.
Marks, get set. Cassie's winning.
Last project, we don't give you Cassie on a Segway, but we give you a planar model of a Segway. And you're going to build a feedback control law that stabilizes it, keeps it upright, and moves it around. And we will pass it through a tunnel of darkness where I have programmed it to apply all sorts of disturbances and try to knock down your Segway. And if you come through, you get lots of points. Okay? So that's how project 3 works. The people down here are those who contributed greatly to the creation of these projects. If you haven't been to our Canvas site, cannot locate the internet server or proxy. Okay, well, I guess we're not doing showing the Canvas site. I'll go through that in the lab, make sure it's working. I'll do that tomorrow in the lab. Okay, and that's pretty much it, Monty. I'll just mention, whoops, why? What do you got? Oh, help Monty, your computer, I've messed it up. Oh, I see. I need to do this. Enable, activate. Yeah, you've got things locked up so that nobody can do anything bad to your computer. Yeah, I thought I was. Shouldn't really matter, right? Oh well. And it's all yours.
Oh, you have more slides?
No, not really. So the final thing is I just want to thank the students from last semester formally in this because the success of the course allowed us to win the Provost Teaching Innovation Prize. So I think you're in for a really great experience. I will be teaching the formal lectures on programming, and Monty here will be doing the lectures. So, yeah.
Okay, can you hear me? Well, it was fun, but unfortunately it didn't last long. Jesse is going to leave, and you'll be with me. Okay. Now the slides that I will use, you can find it on Canvas. If you go to lecture notes fall 21, I try to upload them. I don't know if you will like it. It's okay if we just write notes on papers. Some of my grad students always want to have them and just write on their slides. So that's why I'm doing that. Now the lectures, now I have the same problem. I need to.
Yeah, this is the first time all of us are teaching in this room, so brand new building. We got to get used to it as well. It's not like we're total losers.
And the problem is it's showing, obviously, the desktop, but it will show the PDF if I go to the presentation mode. But the PDF Draw app, I don't think it has that.
You've got it set, your computer on duplicate?
Yeah. Let's try with display.
Yeah, you're going to extend, change to duplicate. Duplicate. Keep changing this.
Yeah, I think. Got tech support from Jesse. All right. Now, if you want to watch lectures done by Jesse, you have all of them on YouTube, right? So it's absolutely fine if you like to watch those lectures. And I, myself, when there are multiple people teaching the same subject, I just see which one I like, and maybe I mix them up sometimes. So it's perfectly fine, but it's good to follow the topics with the class as well. All right, so oh, my pen doesn't work. Great. Anyway. So why, I mean, Jesse gave you some motivations, and you already hopefully convinced that you're in the right place. But from the technology and technical point of view, why linear algebra and why computational? Let's make it a conversation. Maybe you have some ideas we can discuss. I'll give you some pictures. See if it makes sense, because if you see a bridge, probably you don't think about linear algebra. That's the last thing you want to think about. Yeah?
Well, I guess like a lot of concepts around orientation and rotation and a lot of the linear algebra concepts need to be applied to things that use computers, I guess, like Jesse was saying. And so it's important to be able to translate that all of the like math concepts into code.
Yeah, that's a good point. If I may restate it.
Summarize the question for those on Zoom.
They can't hear it?
You don't have to type it, just kind of summarize that long question.
You did? Should I do it?
Yeah, please.
I can't type and talk at the
No,
same time.
not to type, but just restate the question because they couldn't hear it.
Oh. Why linear algebra? Now, you said that, well, we need a way to program and code it into the computer in a way that the computer understands it and we can do some calculation. And hopefully that will give us some answer. So that's a big deal. If you write it on a paper, that doesn't mean the computer will understand it. Now, it turns out this way of modeling using linear algebra is very compatible with the way digital systems work. Linear systems are very easy to code using programming languages, and we have very efficient libraries at this point, too. Once you understand how things work, you can use those libraries. So that's one good reason. Smartphones. How do we use linear algebra in augmented reality or virtual reality?
A lot of that has to do with like tracking, like the velocity acceleration of like people moving their heads or moving the camera as well. So I'm guessing linear algebra allows you to make those very incremental changes so that it makes it look fluid and doesn't get the motions.
Excellent, and surprisingly correct, a very detailed answer. So you want to formulate a problem, and then you want to track the movement. The device doesn't know how you move. There's a virtual world, but it needs to track your movement using some sensors in real time. There are other things going on, but deep down, it comes down to solving a linear system to track and incrementally update the solution. And that, if that's not correct or it's not working well, it's going to be laggy or it crashes. Obviously, it's not a product that you can sell. So it needs a correct understanding of the problem and solving it. Augmented reality is just like that. You have a phone and you want to place an object in a video and the way you can see it and interact with it. Or robotics. So it's this perception and navigation and control system on Mars rover. These algorithms, deep down, usually solving a linear system that Jesse will teach you in the end about model predictive control and how they work. Bridges, fluid dynamics, the way we analyze stress on structures, whether it's a car, it's moving, whether it's a marine structure in the middle of ocean, offshore, maybe it's an airplane, or maybe it's just a static building, a structure. You're analyzing it for earthquake. These are all, once you understand the physics, once you formulate it, it comes down to solving some sort of linear systems. Usually very, very large for something like a bridge. So generally in engineering and physics, that's when we can make things happen. We can finally solve it and get a solution. We usually need a computer and programming knowledge, and that's where the computational view of it is very important. Now, some fun links for you. You can click on them and play. This was I don't have internet. You can click on it, watch it later. This was an important paper in computer vision, building Rome in a day. So the idea was, the problem is a structure from motion. You have your camera, you take pictures from multiple places and views, and you want to stitch them together in a way that you can build a 3D structure. Now, the idea was that if everybody is going around in the same town and taking photos, uploading them on Google Maps, can we just download them and reconstruct the city? It turns out you can't. They spent a lot of time on a computer to calculate that. It took a day, roughly. So that's why they called it building Rome in a day. And that kind of became famous in computer vision. That was a fun paper, maybe 10 years ago or more. And maybe art. Tim Davis, Professor Davis at I think he's still at the University of Texas. He is the creator of a sparse linear algebra library, suite sparse, and we use it a lot in a lot of MATLAB, for example, deep down using that library, or a lot of software that you might not realize, but they use that library. He creates art using matrices. There are lots of problems that you might have different matrices. He tries to visualize them and create art out of them, and they're very interesting. Check out the link. It's fun to watch it. So you might be an artist and use linear algebra to just have fun. So from the mathematician's standpoint, also linear algebra is the workhorse of modern mathematics. So in science and engineering, the core of math and engineering is now linear algebra. That's the starting point. It wasn't for me, even though I'm much younger than Jesse. I think Jesse moved to Michigan when I was born. So he got his PhD way before that. He was an assistant professor. He just moved to Michigan the year I was born. But even when I started learning math in high school, it was all calculus. No linear algebra. So we usually, when we reduce the problem to linear algebra, we're in good shape usually. We know how to solve it. And the problem formulation itself is a big part of your engineering education, because it's really an art of understanding physics and coming with set of design principles and rules, how to formulate a problem. Then you probably want to solve it, and you maybe use a software, and software will do it for you. But you want to understand the principle behind it. And computational view, obviously, because it's going to be for real problems. We don't care solving, obviously, 3 variables, 3 equations. That's when people say that, why do I need math, right? It's not going to get me anywhere. They're right. You got to do it properly, combine it with different skills, and then you can make a living out of math. So what makes you attractive as a freshman? Any thought?
I have an answer.
Yeah?
So I guess like the fact that you're taking like classes that would be generally taught like upper level years, so like taking a linear algebra equivalent class in your freshman year when it's generally taking maybe sophomore, junior year.
Yeah, taking courses that will enable you in the future makes you attractive. Other people want to be connected with you and probably invite you to their lab or projects to collaborate with you. Any other idea?
What do you mean by attractive to who or what? Like university, to other students, professors, to people that might
To research and technology and science communities.
Then I would say that we're taking courses that are more geared toward the future of our field than other students might be taking. Because if linear algebra is, like you said, so important for computational analysis and AI, by taking class freshman year and taking other classes like it, that puts us ahead of our classmates or people from other universities.
Yeah, that's certainly classes like this course will give you an edge, and that'll look very good on your CV. Yeah?
Since we're young, we have a lot of potential to, think about.
Did you cheat? Did you read my slide? You're right. Time, right? Well, that's you right now. Unfortunately, my writing doesn't work, but anyway. So you're like, I've seen faces like the left picture a lot when people stand in line when they want to apply for internship. So, yeah. infinite potential. You guys, everybody thinks that you're going to change the world. You have infinite potential. That's the most attractive thing about you. Courses are fun too, but so deep down, all of you, you have that, right? So you made it through 2020, an admission process. So to me, you're the chosen one, as long as you're here. So you have infinite potential, and you really need to build on that. I mean, it took me a while to internalize this, because when I was your age, I wouldn't believe it. Like, what are you talking about, right? But that's true, because now when I look back to students that I want to work with them, that's what I think about. They have infinite potential. We can do something big. They're young. They have the same motivation that I had once upon a time. So be aware of that. So when you interact with people, you have that potential and you're very attractive to them. They want you to be successful. They want you to do big things. And they like to spend time with you because you have that potential. Time is obviously your biggest asset, then linear algebra and programming. Then you should be able to get a good internship one of these summers, right? So today we're just gonna get the ball rolling and some introduction to refresh some algebra topics that you know already. Then we want to see how many cases that we can face when we see a linear system of equations. We start from a few number of variables, and then we will make it spicy very soon in the next lecture or the one after that. Notation is obviously important. If you are confused with the notation, please ask questions here or on Piazza, anywhere you can find us. It's not that you should assume that everybody knows and take it for granted. Notation is a big problem always. When we use a notation, we have to explain it, and it's always good to use a simple and understandable notation, not making it unnecessarily complicated. So it's not an advantage when somebody uses a complicated notation. So you've seen quadratic equation. Do you remember this?
Maybe.
No, it's not working. So why we call an equation linear? And is this equation linear? Because it says quadratic? Yeah, x is raised to the power of 2. So typically when we say linear, we mean in the variables that we want to solve, we don't see x squared, cube, sine of x, cosine of x, square root of x, right? We usually don't see that. We just see x. B times x plus c, that's linear, right? It doesn't matter for the other terms, right? So just the variables that we want to solve for, if it's linear in those variables, then it's a linear equation from the standpoint of those variables. So you had this idea that calculating delta, and then we could categorize the solution. It's always nice if you can come up with a set of rules, and that classifies the set of solutions, because now we have a structure. We can operate based on those rules and find out the solution. And in fact, you can automate it. Once you have a rule, you can automate it and you can program that in a computer. So you would say if delta is bigger than 0, you have 2 distinct real roots. Repeated roots if delta is 0, and you could have complex numbers if delta is less than 0. If you don't know what's complex number, don't worry about it. Oh, I can write now, but with my finger. All right, so for the, yeah, I was going to ask you.
I don't know.
I think so, yeah. Something is wrong with this.
Yeah, battery's dead.
It doesn't have a battery.
Yeah, it does. Sorry, or not charged.
Can I keep this? Okay. So, what can we say for linear systems? Which you might not have a good idea what I mean by linear systems, but we're going to make it more concrete today. So we can have no solution, we can have a unique solution for the problem, and we can have infinite number of solutions. So it's only going to be one of these three cases. Case 1. Suppose we have these two equations, x plus y equals 4, 2x minus y equals minus 1. How would you solve this? You might have a way of solving it. It doesn't matter what way. But maybe this is the best way. Now that we have only two variables, we can visualize it. If you have three variables, you could also visualize it. More than three, good luck with that. That's why then we need to make things a little more abstract. We need just equations. But we understand what's going on. It's just hard to visualize it. The concepts will carry over to higher dimensional spaces too. So you might think about x plus x equals 4 as a line, the blue line. Is everybody comfortable why this is a line? Because if you're not, you probably want to practice and visualize them, to reproduce this graph, and then when you're stuck, ask questions until you can do it. But the idea is simple because you can say, well, y equals minus x plus 4. Let's say x is 1, right? Y must be 3. If x is 0, y is 4, right? So that gives you 2 points, and connect 2 points, you get a line. That's how I plot a line. A harder way is that you have a slope here, and then you have y-intercept, and whatever else you learned to plot this. Now you do the same thing, and two lines are intersecting. That's very interesting. The solution, I'm going to claim that the solution is the intersection of these two lines. Is there any objection to that? Why that's a reasonable claim? Because we are not doing algebra, we're just playing with geometry here.
Well, we're working with like two variables, and we're working on like a 2D space. The way that we figure out where the equations would equal each other, that would be at a certain coordinate of x and y. So,
right, so you're saying that we want these two equations to be true at the same time. If each of these equations is visualized as a line, we convert it into a geometry, a line, then what is the case that both are true? Wherever they're occupying the space at the same time, right? For two lines, it's just the intersection of that. So that's the intuitive way to prove that that's the answer. So, and it's unique, right? Two intersecting lines, you only get 1 point. So the solution is unique. Now you could use an algebraic way of finding the solution, no visualization. You would say that I'm going to first find x in terms of y, and then I'm going to substitute it in this equation in place of x, and I'll get myself an equation that only depends on y some manipulation, you find the answer. Once you find y, you can go back and find x because we already know x is 4 minus y. You get 1 and 3, which is exactly the same point on the graph. You can try as a practice the other way around. First, solve y in terms of x, and then substitute it into the equation and see if you get something different. If it's unique, by definition, you should get the same answer. Otherwise, something is wrong, right? The claim is not correct otherwise, because we claim the solution is unique. So another trick is there's nothing that can stop us from adding these two equations, right? Together, we can do that. There's no rule that says that's wrong. And once you do that, y gets canceled. Then you get an equation that only depends on x, then you find the answer. And once you have x, you can use either of these equations to find y, and you should get the same answer because they are both true at the same time, and that's the point on the intersection of two lines. So we say mathematically that the solution, the set of equations has a unique solution. That's the formal language you can use. And it's very convenient to stack them in a vector. This is your maybe, or maybe not, first encounter with a vector. You could use this notation. Jesse explains these things in the book. Chapter 1, it's all about these topics. Don't panic if you see somebody calls this a vector, that's okay. I prefer this case. I think Jesse prefers that notation too. So we prefer in Michigan that notation. By induction. That's 501. I think they teach proof by. Do you teach proof by induction? So if you want to learn formal proofs, you need probably more advanced math courses. But this notation is, I don't know, it's prettier probably. Use bracket, but you could use this one too. So when you stack them together, this equality sign means x equals 1, right? Y equals 3. But this is probably a little redundant, so it's much better to just use one equality sign. Case 2. Do you have any questions from so far? Right.
Yeah, just a question about the formatting of the matrix. Would it still make sense if you didn't stack them and it was just x, y in the brackets side by side and then 1, 3?
Very good question. So the question is, can we just write them like this, right? Or did you mean something else?
I meant something else. Like, still inside of the brackets, but instead of x and y being above and below each other, it's the left and right of each other. As long as there's
oh, you mean
characters, would that still be the same thing?
Like this?
Almost. So.
Or like this?
Yes.
Yeah, so we're going to talk about it later when things are a little more serious and we get to know each other better. We're going to talk about row vectors and column vectors. So this is something you would call stacking in a row. This is a column vector. No. Both are correct. You need to choose one and stick to it usually if you're trying to do some manipulation. You cannot just change the convention halfway through manipulation. That makes it usually incorrect. But other than that, it's just a preference. It's very common to use column vectors as a default. Occasionally, in some math books, you might see they stick with row vectors, but in engineering, it's safe to assume that 100% of time, column will be the default, right? So no difference. It's not going to change the value of the variables, right? The way we stack them. So most of these things that we talk about in this class, it must have some sort of intuitive and obvious explanation. If you find it not obvious or counterintuitive, please ask questions. So maybe we can find an intuitive answer for that. So same number of equations and no solution. Why we might have no solution based on 2 lines that we had? Now, first of all, we might recognize that if you factor 2, so the left-hand side of the second row is just twice of the first row. No difference. However, the right-hand side is not the same. Again, we are allowed to multiply 2 sides of an equation with any non-zero constant. In principle, it doesn't change the solution. You can try, for the first example, multiply it by any number you want and try to solve it again. It should not change the equation. You can think about it as having 2 masses on each side, right? If you add to both of them same amount, or it's a basically scale, it's not going to change the equilibrium, right? That's the idea. So that's a little strange, right? It's a little suspicious because we multiplied the left-hand side by 2, but the right-hand side is not multiplied. So the balance is broken. So we expect something exciting shows up. And in fact, these equations are inconsistent. And the exciting thing is that these lines are parallel. Because the left-hand side are similar, and the right-hand side, if you think about the equation as a line, it's the y-intercept. So it just shifts the line up and down. So they are parallel, and 2 parallel lines, as far as we are concerned, they don't intersect. You take a computer vision class, they'll tell you, no, they do. Because of the projective geometry. When lines go through your camera lens, they do intersect, but for now, we don't work with that. I think Jesse has some camera calibration notes in the book and some projects maybe in the end about that too. But we don't deal with that. So parallel lines, no solution. They will never intersect. Now you can try to solve these equations. We had a way of doing it. Let's try that. Find x in terms of y, substitute it back into the second equation. We reach a contradiction. 2 equals -1. This is when your computer goes crazy. But not because of this. If you check this, it will tell you it's false. We'll learn a more advanced concept to give you superpower. It's called determinant. It'll come up later. It's like a division by 0, right? Computers don't like that. When you do that, you get an error. Okay, so we have a contradiction here. This does not make sense. And formally, we call that there's no solution. The third case is when we have an infinite number of solutions. It's just anything that you pick is correct. So there's no case that you have 2 solutions or 3 solutions. It's either one unique solution or as many as you want. That's the possibility here. So this time, the right-hand side is actually correct, we recognize that the second line is just twice of the first line. And in fact, even though we are given two equations, by looking at it, we recognize that they're the same. So in fact, we have one equation. So we are not given any extra information beyond the first line. And what do you think happens if you plot them? Perfect. So two identical lines. This proves that if you multiply two sides of the equation by a constant, non-zero constant, it won't change it because the line remains a line if you plot it. That's a good way of proving it yourself. Convince yourself that that's true. The blue and red lines are exactly the same. And because of this continuous intersection that they have, it's just there are many solutions. Two lines are coincident. Now you try to find a solution using the same method by substituting from one equation to another one. You end up with a conclusion that is perfectly fine. But it doesn't tell you anything. It's just always true. That is usually not useful, right? If I tell you if you don't breathe, you will die, I'm not giving you any information. You know that already, right? That's not helpful at all. So mathematically, it needs to add some sort of extra information or you will not find the solution. That's always true in all the math problems we will study. Okay, so now one way to describe this is pick one of the equations, say, now x equals y plus 1, and y can be anything from minus infinity to positive infinity. If you remember, you would call this the set of real numbers. Real line. This could be 0. And then it goes from minus infinity to plus infinity. So anything you pick for y is correct. It's true. You're not going to violate the equation. And then you find out what's the value of x, which is essentially a point on one of the two lines you had. Now, physically, this is not helpful. If you're designing a product and then you have two variables, you need to make a decision, right? It's nice that if you're designing an optimal product, maybe you have enough constraints to pick something that is more intuitive for you and then find all the other variables. But if everything is open and you can just change it, that usually doesn't lead to an optimal design in engineering. You can give physical meanings. If you like more physical intuitions, we can always try to find something that connects to the equations. All right, so you could do the other way. You say y equals x minus 1, and then x can be any value. These are equivalent. They're exactly the same. Okay, so any questions so far? These three cases, we will just generalize it, make it work for larger scale systems using more advanced tools. But the concept, the idea behind those cases is exactly what we talked about. You could draw these with planes. In three-dimensional space, a line, equivalent of line is a plane. I think Jesse has a picture of that in the book. You could see that. I'm just using lines because it's simpler to talk about it. So to summarize and introduce some notation, we can write a system of equations in general to be something like this. Now, A, 1, 1, 1, 2, 2, 1, 2, 2, right? These are coefficients. These are the constants that we use in the equations, and then you have B1 and B2. Why we're using now letters instead of numbers? What's the point of that? Okay.
Generalize your concepts to make them easier to understand, but not nail them down to a certain value.
Right. So we want to generalize that they look like this form, but a number can be anything. This, for example, the first coefficient, 1, 1, can be -2. Now, I don't want to write numbers because they can be anything, and then we have to analyze the system of equation based on particular values they will take. But once we use some symbolic calculations to lead to computational formulas, then it's general usually. And about the indexing, now this will it will make more sense once we talk about matrices and vectors, which is next time. But I'm going to tell you that this is the correct way to do it because it's consistent with what we want to do with matrices. So you could think about it that this first one, it's about line 1 here. And the second one is about this column 1 here. So you have column 2, you have line 2. So line 1, column 2. Line 2, column 1. So it's not random. I didn't randomly assign indices. It makes sense if I just, in other words, if I just give you these guys, and I tell you to write a set of equations for me, you can do it. You know where to put them. That's very important. We have a common language now to communicate. There's no misunderstanding. There's only one way to do it after we agree that this is how we're going to do it. Okay? And X and Y obviously can be W and Z. So that's also not a problem. I think at this point, Jesse was talking about Greek alphabet last year. And some of you might not be familiar with Greek alphabet. That's fine. Not very difficult. We don't want to speak Greek. We just want to use the alphabet, alpha, beta. Generally, any letter is fine. It's not about the letter. Sometimes we just don't have enough letters in the alphabet, and we might borrow from another language. Okay, to summarize, consider this system. It can have no solution, it can have a unique solution, or it can have an infinite number of solutions. Okay, one question, why? We have until 2:50, right? What does it mean? Like, I'm telling you, that's typically a problem in math courses, right? I'm just telling you this is a fact. Later, we're going to prove it. What does it mean if you are dealing with this in engineering? Or you're actually studying a physical systems? What's the implication of statements that I'm telling you? You can just drop ideas, right?
In respect to the region, not defining the coefficients? Or like
Right. For a particular problem, you know the values of coefficients, right? Left-hand side, right-hand side. You want to solve for the variables. And maybe you have the tools already, and then you can verify that, okay, there is a unique solution, or there's no solution, or There are infinite number of solutions. Now, what's the implication of that?
I have an idea. So maybe like with the unique solution, like sometimes you might be trying to optimize some certain algorithm, and if you find the unique solution, that might be the optimized solution.
Yeah, so it will reassure you, right? If there's a unique solution, everything is correct, then what you're doing is correct. Hopefully, it's not everything, but assuming your model matches the reality for the good part, then you're in good shape.
Just along those lines, if you have working with many different equations, and you find two equations that they have no solutions with corroborating variables, you know that they are parallel, not parallel, but you know that they do not interact. That's the no solution point. And then the infinity of solutions would be you have two equations that may look wildly different, but they are in fact the same equation.
Really, really interesting explanation. So the first one, you said that if you have no solution, right, that means that that was the case, the lines were parallel, right? That means that you think you have two different variables, but they are not basically telling you more in the sense that they're just pointing towards the same direction in the space. So if you imagine there will be another direction orthogonal to that line, if we just think about it that way, right? Then there's no way we can move orthogonal to the line. We can only move along the line. So clearly we're missing information along some dimension in the system, whatever that might be. From the physics, you might get the knowledge about that. And the infinity of solutions, you said that we might have equations. Maybe sometimes this is a scary equation, right? They look different. And you look closer, and then you investigate. It turns out you can simplify, and they're actually the same. And it's very dangerous, right? If you naively operate with them without knowing what's going on, what if that leads to some instability if it's a structure or something, right? Things can have real consequences in the physical world, right? If you're manipulating math to design and build something, then it obviously has consequences in real world. So there's no shortage of meaning behind these equations. But the beauty of them is that they're general. We can study them in the abstract sense, that we talked about them now, and then you can connect them to realize them for different problems. That gives you a tool that you can apply in many cases. That's very powerful. Now, what if we have 50 variables? Like instead of x and y, now I have 2. What if we have 50 variables? How would you solve that? You find them one by one and substitute?
No.
Okay, I think I misheard.
I listened to Tom, and it would take a long time. But
It will take a long time, you're right. And that's conditioned on the fact that you're willing to do it. Right? Trippy, you?
Someone suggested use matrices.
Great idea. That's what we're going to do. So we clearly lack some more knowledge and tools and way of formulating the problem so we can scale it up. Scalability is a problem. So just writing it in a line and for 50, 100 variables is not going to cut it. This is just annoying, and nobody wants to solve that. We like it for 2 or 3 variables. We understand what's going on, but we want to generalize it and not bothering with hand calculations so much, right? Because we want to do creative work. We don't want to be calculator. We can use computer for that. But we also want to understand, when we get a solution from a computer, we want to look at it and then understand if that's correct or not. Which that's what differentiates you maybe as an engineer or a physicist or mathematician from maybe a person who's not trained. So 50 variables, we're in trouble. We can't do what we did. What about the letters? How about we do this? How do you like this? Put 50Z next to each other. No? Nobody in favor of this? These guys are smart. So, yeah, obviously that doesn't make any sense. It looks ugly and confusing. At some point, you're going to make a mistake. That's for sure. So a simple solution is indexing, and surprisingly, it's compatible with how computers store variables and vectors. You just use indices, and Jesse will teach you in the lab, and a lot of you probably tried it already. And then you can use indices to refer and restore that number in the computer, and it's perfectly programmable in this way of writing it. So we use index. Now instead of saying x, y, z, w, you can just use x and then say x1, x2, x3, xn. Now n usually is a natural number, 1, 2, 3, 4, any number, right? For example, 50. Okay. So we covered the ground rules as well, and that's all I have to talk about for today, but we have time for questions and discussion. Now, I give you reading each time. Today was about chapter 1, so maybe you read it, or maybe not, but it's sort of more about the background. So you can take a look, and please ask your questions on Piazza. We have a lot of office hours. Don't wait until you have, huge problem. Even if it's simple, that's really good if you ask it. Piazza is really good because your friends can answer, you can interact, and we don't have to answer the same question 100 times. We're happy to do it, but obviously we could use resources better, right? That's our job to answer. We're not going to be unhappy about it, but we can operate more efficiently. It's more scalable. So read chapter 2 for the next time, and we're going to talk about vectors, matrices, and determinants. And the key is we can write it in a way that is scalable. We're not going to learn how to solve it, but first we have to learn how to arrange equations in the right order. So is there any question for today or any of the topics? I can go back. No?
Any questions for me? Lonnie's going to be doing
Yeah,
most of the lectures.
for any of us, yeah. It could be about any part of the lecture. Yeah, go ahead.
So do you read it in the next section?
The chapter 2, it's great if you read it. I mean, if you don't read it, obviously, I'm not going to come and check. But because it will be very exciting when you read it. Maybe there are part of the book that you don't follow or it's not clear, which you can always give feedback to Jesse to add more information. But then you could ask questions. And when I talk about something, you ask questions, and that'll make, ideally, the lecture will be a conversation, not one-sided. That's the preferred way of carrying it.
Yeah, I mean, it usually takes multiple passes for stuff to stick. I mean, I think most of us would not just, if you're playing an organized sport, for example, you wouldn't just look at a play once on a diagram that a coach does and then think the team is going to go out and execute it perfectly, right? Oh, yeah, we've seen it on the board, okay, we're definitely going to do it. Or I watched a couple doing dancing and I'm going to do the exact same moves just by having watched once. It takes, you got to re-imprint things. So if you kind of scan to see what's there, then when it's up here, when you saw a point in the book that wasn't working really well, you go, oops, it didn't work for me here either. So that kind of helps out. And then if you maybe print out the notes ahead of time and you write some questions on them and stuff, it'll help in print. And then the homework is what really gets it going.
I intentionally leave a lot of white space in the slides, because if you print it, you can write on it. That's the motivation behind it. Yeah.
You want to connect to the Wi-Fi and I can just show them where they can find the lecture notes in case they didn't get it?
Yeah. It's
Probably easier with you.
I hope Microsoft sells the pen separately. Otherwise, I have to borrow this every time. Oops, connecting. Well, I did bring my iPad as a backup.
There we go.
I think iPad works too.
Yeah, EDU Rome was down. I had to go to M Wireless this morning. I don't know what's going on. If you're on M Wireless now, it should work. Yay.
Yeah, I actually had Canvas open.
Fantastic. Okay, so, whoops.
Oh, you.
Yeah, I'll just steal this. Because online it's hard to hear if we're not mic'd up, and you'll see the video recordings. When we're not mic'd up, it's really hard to understand. So this is the Canvas page. And announcements is where we'll just put the general things out. So this was the welcoming announcement, etc. Under lecture recordings, that's where today's lecture will show up in about half an hour. Okay, so you can just watch it. Those of you who skip class and trying to catch up, you'll watch it at 1.5x, we know, okay? But just, your students, your mind is very young and fresh. This will help give you an idea of when things are due. That's there. Illumi-Desk, I will explain tomorrow. Gradescope, we don't need yet. Files. So here's the book. It's right here. Everything. Whoops, I didn't need to go back. This is useful. So if you want to just kind of see where you are, it's basically telling you the topics that'll be covered. Excuse me, question.
I have a question. If you scroll down to, I think it's week 7 on this, looks like there's some sort of a typo on there. Where like week 8, part of week 8 is written on week 7.
And if this is the correct, maybe I need to update it.
Yeah, it's right there, week 7. You've got quiz 4 due 10/21, but it's written in 10/14 area.
Let me double check that. There's the fall break that's in here, and that's probably what's messing things up. But let me double check the dates. Okay, but yeah, okay. So at least I think the first several weeks should be good. Let's see, notes from lecture. So this is the file that Monty was working off of. Okay, so you've got those. You can look at it. I mean, if he's going too fast for you to get something, you can have it open on your computer and do something a little bit slower. That's fine too. This is all the material from Fall 20 made available. So you've got the lecture notes. And, you know, I'm old-fashioned, right? I mean, as Monty mentioned, I joined Michigan in 1987, his birth year, okay? You know, I'm used to having, I was really sad for me the first time I realized I had students who were born after I earned my PhD, then they were born after I made tenure, then they were born after I was promoted to a full professor. So these are the notes. The good thing is they're very colorful. Whoops, okay. The bad thing is you had to watch me write them all out by hand. So I don't know what you guys are used to and prefer if the class comes to a consensus, but A lot of the material is pretty much the same. There's even the teaching evaluations there, etc. So a lot of the stuff is there. Can we open up the Rob 101 thing from last year? Is you have that accessible?
I think it's.
Yeah, it should be right here on your homepage. It is in mine.
Oh, here.
Yeah. So.
Okay, you want to go to the website?
Well, I just want to show them Piazza because Piazza is much more exciting when there's stuff on there. Logging into Piazza. So Piazza allows you to just do text if you want, but you can also do lots of different math things and stuff. And so really Piazza is an ongoing discussion. If you have questions, it may be a little bit hard to read, but up at the top, there's things like this is questions on Project 3. All of the Julia and Jupyter notebooks, there's different topics. You just do a topic, and then you create a new post, which we shouldn't do because this is from last year's course. You can select your thing, you put a summary, and then you just write it. And then what you would want to do is if you know the answer and you can help someone, it's 2 in the morning, probably I'm not online, and maybe Monty's even in bed by then, since he's the ripe old age of. Go ahead and help each other. This is what it's for. So in terms of collaboration, engineering is a team sport these days, okay? It's all about collaboration. You can collaborate as much as you want on homework. You should still turn in your own work and know what you're doing, but just find to form groups and do homework. And that's true for the Julia homework as well as for the drill problems. There'll be quizzes, which you should do on your own, but they'll be posted for a week. Okay, those you should do on your own. And then the projects should be mostly your own work. If you have questions, you post them on Piazza. That way everybody sees the same thing and stuff. But Piazza is this ongoing discussion to help us learn. And if you know LaTeX, you can put your equations in double dollar signs and get the nice matrices and vectors to show up. It's kind of cool. And if you don't worry about it. We don't care. We just want to have the conversation. And then for doing your programming assignments, it'll be through a LumiDesk, and we'll go through that tomorrow afternoon. Question?
So the question online is, do we have the lab tomorrow or do our labs start next week?
So labs start tomorrow. Yep, we'll learn how to use Julia as a calculator, plotting, etc. And as I posted on the welcome email, there's no pre-lab and there's no post-lab, okay? So, yep, another question. No, we will talk about that in class. It's nice if you want to bring a laptop or sit next to somebody on a laptop. It'll be a lot more fun to do it collaboratively, but otherwise you can just watch here and then you can go home and go through the exercises on your own. It's up to you. But I think bringing a laptop, pretty soon Kane is supposed to have where you can check out laptops if you don't have one. So.
You can use browser to code.
Yeah, you just access everything through a browser. You don't need to install anything. You access everything through the LumiDesk tab in Canvas, and we'll hope it's working tomorrow, right, Tribby? It's working most of the time. They've got their reliability up. So, anything else? Okay. We have 1 minute to spare, Monty.
Yeah,
over and out.
Just the last thing I want to say that, so my office hour is, it says 1-on-1 meeting. Now I can set a time too, but historically, most of the time, I just sit by myself. So I want to be flexible. Whenever you want to meet, just send me an email. We can meet. Obviously, I'd love to talk with you. And don't feel bad if you're meeting once or twice, you want to talk more, it's usually not a problem. But we'll find a common time and then we meet. Jesse Trippi will have regular office hours, and you can just show up and ask your questions. Thank you, and see you on Wednesday.